Okay, so we've reached this stage where we've got the solution for y bar, and this agrees with the one that was given in the question, so we're confident that what we've done there is okay. So, okay, any queries or questions about getting to this stage? Are you happy with how I did it? So now we're looking for partial. Should we do that now, or should we collect? Let's go back and obtain x. No, that's not. Let's keep going. So now take partial fraction expansion here. We'll take partial fractions before the inverse transform. So we have y bar. Now I've got an irreducible quadratic factor here. So I've got s squared plus 1. I've just a constant on top, so I'm just going to have something like as plus another constant b over s squared plus 1. And this is going to be plus another constant c over s plus 1. So this is going to have a partial fraction expansion of this form. Remember, when you have an irreducible quadratic factor here, the numerator needs to be of order 1 in the variable. So constant times the variable plus another constant. Bring this back together again. Over that. So you'll have as plus b times s plus 1 plus c times s squared plus 1. So we're going to see what happens to the a, b, and c. So multiplying s squared, you've got a plus c times s squared. Multiplying s, you've got a plus b. And the constants, you've got b plus c. Is that right? So it's very much a recipe. I'm going to set procedure this. You're comparing this back to the original numerator. You're comparing this to up here. It's a 2. So this polynomial in S must in fact be 2. So comparing this numerator to 2, we get that a plus c is 0, so is a plus b, and b plus c is 2. Someone's saying minus 1 for a, 1 and 1. Yes, well spotted. So a is minus 1, b is 1, and c is 1. So if you can't see it simply or by substitution, or you don't have someone helpful in the audience telling you what the answer is, you could use a Gaussian elimination, okay? Because that's what it is. It's just a system of linear equations in the unknown, so you will always be able to get the solution to it. So this gives me y bar as minus s plus 1 over s squared plus 1 plus 1 over s plus 1. And these should be on the table. One over s plus 1 is going to be an exponential. It's then minus t. And this s squared plus 1 Well, this is going to be a combination of, so you look at the denominator first, s squared plus 1. Where do you see things like that? S squared plus 1 in the denominator on the table. Well, they're up here. S squared plus omega squared, S squared plus omega squared. So this is going to be a sine and a cosine. But for the cosine, you need an s in the numerator, and for the sine, you need an omega. So we've got omega equals 1 here. So we just want to emphasize that this is minus s over s squared plus 1 plus 1 over s squared plus 1 and plus 1 over s plus 1. So that really explicitly gives this now as a combination of three things, each of which is on the table. Okay, so now we can take inverse transforms. We'll take the inverse transform of both sides. Bit of a catchphrase, using linearity and results from the table. This gives us, as on the left-hand side, we'll have yt, taking the inverse transform y. And the s over s squared plus 1 is a cosine, so it's minus cosine of t. Omega times t, but omega is 1, plus sine of t. S plus 1 goes to e to the minus t, plus e to the negative t. So that's the y coordinate of this particle, time t. There was a bit of the question talked about steady state and transient components of the solution. They're in the notes slightly further on, but these terms here are called steady state. These are, let's say, just say they're always present. This term is called transient because it converges to 0 as t goes to infinity. It's not always, well, it is always present, but it's diminishing all the time. Its influence is decaying away. So that's called transient. Of course, that's just the y coordinate. Yes. No, it never does. So, okay. Yeah, but it's as distinct from these, like these two, while these two wax and wane, because cosine does go to 0, but it's substantially it's always around. Whereas this is converted, after a certain amount of time, you could safely ignore this. If you were looking just for approximate answer, if you were satisfied with a certain level of accuracy, after a certain amount of time, this term could be forgotten because it would have gotten too small. Yeah, but eventually if it's converging to 0, eventually the transient would become way, way less than it, even if this was times. I mean, they're just descriptive terms at the end of the day. But it's just pointing out that the effect of this is substantially different from the effect of these. Yeah, in that sense. Yeah, first. What if t is pi? Root 2 over 2. Oh yeah, well, so like for certain, yeah, so at special values of pi, at special values of t, sine and cosine agree. so it goes 0. But that's just for that one value of t. Once you go past that value, these two terms emerge again. So yeah, if you graph these two, you'd see the cyclical graph. And at certain times, yeah, it is hitting 0. But it's always around. The influence of these two terms is always there. They never disappear after a certain amount of time. Whereas this term is, after a certain amount of time, this is going to be gone. So we ought to find the x part of the solution. So as I said in the last hour, we've got a couple of approaches here. We can either go back to this C and D, because I know what y bar is now. So let's do that for this time. Or I could, if I wanted to, take what I know about y, my solution now, and return to one of these ODEs. And put in the solution y, and then in fact you just have, because it's only a single derivative of a certain order for y there, you should be able to just integrate both sides to obtain x. Well, I did it using the original ODEs last time, so maybe this time, just to display something different, what we shall do is return to equation C, which I labeled earlier. We'll return now to equation C. C implies, so we know what y bar is now. S squared y, well, C is S squared y bar minus S x bar equals 2 over S. So this implies probably going to regret this, but this is minus S x bar equals 2 over S. And then when I send those over the other side, I get plus S cubed S squared plus 1. Minus S squared plus 1 minus S squared S plus 1. Okay, so it's using the y bar that I found a few lines ago. But then I need to divide by minus S to get x bar. So it seems to be minus 2 over S squared plus S squared over S squared plus 1 minus S over S squared plus 1 minus S. Oh no, I'm dividing by minus, so I'm changing signs all the time. Plus S over S squared plus 1. Isn't that right? Yeah. That's right. S plus 1 on the bottom. Sorry, yeah. Thank you. So I need to sort myself out here. And the minus 2 over S squared is fine. So this minus S squared over S squared plus 1, well, really that's S squared plus 1 minus, let's just write them like this, S squared plus 1 minus 1. that s over s squared plus 1 is okay. That's on the table. And lastly, this is s plus 1 minus 1 over s plus 1. And so when I have them like this, I've got minus 2 over s squared. So this gives me a minus 1 and then a plus 1 over s squared plus 1. This gives me a plus s over s squared plus 1. And gives me a plus 1 minus 1 over s squared. So actually that plus 1 and minus 1 are going to go. So the reason I attacked those two like this is because those weren't yet in the form of things from the table. Because they had numerators of equal order compared to their denominators. So you're just basically dividing the numerator by the denominator. So what have we got left? Let's just write it down once more. So we see clearly it's minus 2 over s squared plus 1 plus 1 over s squared plus 1 plus an s over s squared plus 1 minus 1 over s squared plus 1 over s plus 1. So now this is a linear combination of these four things, but all four of them are there on the table. So now we can take inverse transform both sides. Okay, I won't repeat myself now, but we're using the linearity principle and taking results from the table. We're going to get x of t now is minus 2 times, so 1 over s squared plus 1 is a sine of t. Oh, I should have combined those two, shouldn't I? So it's just a minus sine of t. Sorry, whoa. Sorry, I added in that plus 1 there. So sorry, inverse transform of something over s squared goes to t. So this is minus 2t. I've got a plus sine of t. S over s squared plus 1 is a cosine t, and then I've got this exponential minus e to the minus t. So that's our x coordinate. And again, using that terminology, these terms are steady state. So you can't really forget about these. But this one again is transient because it's, after a while, it'll be ignorable. Is that okay? So I probably could have done that a bit more efficiently. Any queries about that? The line above, up here. So what was I doing here? So, well, these two, we need to do something because these two, as they stand, aren't on the table. You don't find anything with those denominators and those numerators on the table. So something must be going on. Why they're not on the table is because it's possible. Basically, I'm just finding the partial fraction expansion of those two. That's another way to say it. The partial fraction expansion of s squared over s squared plus 1 is 1 minus 1 over s squared plus 1. So I recognize that if I added 1 up here, then I get exactly the denominator. So I can add 1 and take away 1, keep an equation. Similarly here, if I add 1, I'll have exactly the denominator. But I'm adding 1, so I must take away 1. But then, you see, s squared plus 1 over s squared plus 1 is just 1. You have 1 minus 1 over s squared plus 1. Similarly here, you've got 1 minus 1 over s plus 1. So it just gets everything, just boils everything down to things that are found in the table. Any other questions? So we could say all parts of solution have been found. Okay, let me just go over here. Let's just do one more. Not one like this, but one that looks in closer detail at some inverse transforms. So this is again from a 2002 paper. So this question was find x of t given that the Laplace transform of x of t is 3s minus 1 over s squared plus 6s plus 13. As 2002 is when I finished my PhD. What are you guys doing in 2002? Cycling around on your bikes or kicking balls around? So what we have to do, well, really we just have to take an inverse transform. So we have to look on the table for this function. Okay. But now a first examination of the table means initially you think, oh my God, I can't find this. Okay. But this is because when you look at this quadratic, this is a irreducible quadratic, isn't it? Because if you look at the discriminant of this quadratic, b squared minus 4ac, it's 36 minus 4 times 13, which is certainly negative. So there are no real solutions. So the denominator is irreducible. Over R. But irreducible quadratics are here. They're all there in those bottom, and it features an s part as well. It isn't just an s squared plus a constant. If it was s squared plus a constant, it would be one of these ones up here. So the functions with irreducible quadratics, which do have s terms, do have order 1 terms as well as s squared terms, they're these 4 ones down here. Okay, so it's going to be one of those. But there, those quadratics are presented in this alternative way, this kind of completing the square way. Okay, so we need to re-express the denominator. So we have x bar is 3s minus 1, and it's only after we've done the denominator that we'll figure out what to do with the numerator, really. So this is going to be s plus something all squared plus something else, maybe minus something else. So when I square that, I get s squared, and to get the 6s, I need to have a 3 there. Give me 6s. But when I square it, I get 9, but I need 13, so I need to add 4. So my a here is 3, and my omega is 2. And I'm adding on my omega squared, so I'm reduced to looking at these two now. So it's going to be a combination of exponentials times a sine and an exponential times a cosine. But I must take this now and make it match a combination of these two. So here's where I'm going to put the s's. Now I've got 3 s's. So I have an s there, but you see, along with the s must travel the plus a. So I need to put the plus a. I need to put the plus 3 there. But of course, that's going to generate 3s plus 9, but really it's only minus 1. So in order to compensate for that, I'm going to have to subtract 10. This will be minus 10 over s plus 3 squared plus 4. And now I'll just rewrite it again. Yeah, so this is 3 over s plus 3 all over s plus 3 squared. I'll write the 4 as 2 squared, so that's how it appears in the table. But when you've got a constant over that, the constant, you see, you want to express the constant as omega. So this is going to be minus 5 times 2 over s plus 3 all squared plus 2 squared. So you have to kind of prod it, push it, and work on it a bit so that you can see it as a linear combination of things that are on the table. Okay? That's what was driving me. Why did I take this nice, simple single fraction here and bother to write it like this? Well, I did that because that is on the table, as is this one here. Okay, so you just have to tease it out a bit, bring out the ones that are on the table. So I can now take inverse transforms. So we inverse transform this to get x of t on the left-hand side. And it's 3 times, so that first one is e to the minus 3t cosine of 2t, cosine of 2t. And then minus 5 e to the minus 3t sine of 2t. Excuse me, sine of 2t. So this can happen sometimes when you're solving these ODEs, that you may get the transform function, well, in this form here. So this thing here could be the end thing that comes out of the partial fraction expansion. But you still need to work on it a bit before you can read off the results off the table. Okay? And this is an example of doing it for this particular one here. So you've always got half an eye on the table to guide you towards, you want to express your x bar as a combination of things, a linear combination of things from the table. You can then take the inverse transform. Okay, any last questions from any of you? Okay, we'll leave it there for this evening. And I'll see you all at various times.